Ah, that should do the trick. Does that do the trick? How do we know?
Yes. Yes is the answer.
Yes, excellent. Right.
Is that from you or from from the chat? Okay.
Okay, where was I? Oh yeah, I was telling you what causes high temperature superconductivity. So the way I look at this phase diagram is we've got some antiferromagnetism here, and if we start from this side, then as we approach this point here, the antiferromagnetic fluctuations grow, and so pairing for superconductivity grows, and it grows until you reach this point here, at which point parts of the Fermi surface start to become incoherent, and that reduces TC. So from that perspective, the most important part of the phase diagram to study is this part over here, and all this part here is some irrelevance where there's some competing phases. Okay, that's a little bit controversial. But nevertheless, I've also spent much of my life also studying this side of the phase diagram also. Okay, so I've put some questions here. So one is there a quantum critical point near optimal doping, or are there other quantum critical points? And if so, do they have any relevance to superconductivity? So that's a clear question. And then in the endodoped part of the phase diagram, what's the relevance of the charge density wave and the pseudogap? I call them ordering tendencies rather than phases, because that's my view. And this talk is really going to look at what's the electronic structure of the normal state in which superconductivity emerges, and how does it vary across the phase diagram. And so we're going to tackle this problem by looking at electronic transport at high field, in particular the Hall effect and magnetoresistance. And for reasons which will become clear, we're mainly going to concentrate on this overdoped slide here. So, as I said, there are many possible quantum critical points in the cuprate phase diagram. This is a little bit of a joke here, but nevertheless, these are the potential things. So there's one that's pretty much clear here, which is the quantum critical point of the antiferromagnetism. There's a charge density wave phase in the endodoped state, which has potentially two quantum critical points, but whether it's really a well-formed phase in any case is a moot point, and also a point of contention, and certainly there's little evidence really for a quantum critical point. There's also a possible quantum critical point at the end of the pseudogap phase, which is traditionally around 0.19. I think is slightly changed. And then there's another one here, which would mark the end of the strange metal regime. I'll explain about that in a minute. So the point is, do any of these things have anything to do with high temperature superconductivity? So you might think that perhaps if you look at the analoging things like the iron-based superconductors or the organics or the heavy fermions, then the one that's probably most relevant would be the one here. But it could be actually that the one that's most relevant is in fact this one. And this is some other stuff that's happening in the endodoped part phase diagram. So let's just review some of the sort of classic features of the normal state transport. So perhaps the most famous one is that the resistivity varies linearly in T. And so that happens in of course, many elements at high temperature. But the thing is here that in cases, and this isn't one of them, but in cases where the superconductivity is suppressed, then certain dopings, this seems to extend down to very low temperature. So it doesn't appear to be an obvious energy scale associated with this scattering. The other thing is that the Hall coefficient is very strongly temperature dependent, particularly at optimal doping. Okay, so this was the sort of state of play around 1990. And in fact, this is some data actually from my PhD thesis. What I just told you about the linear in T resistivity, etc., is strictly only true at the optimal doping composition. And as I decrease the doping, then we still have a region where at high temperature it's still linear, but then there's this decrease in resistivity below that, which we've come to associate with the opening of the pseudogap. So in the overdoped regime, the resistivity evolves in a different way, in the sense that it starts off being linear and then becomes more and more varying like t squared, like a traditional metal, conventional metal. Okay, so if we look at the if we were to assign sort of power laws to all of these things, then we can draw a phase diagram. And this is some work by Martin Dreven et al. And so here they've shown the underdoped part of the phase diagram. So you have a regime at high temperature where you have this the resistivity varying linearly in temperature, a sort of intermediate region, and then a low temperature region where it varies like t squared. That's in the underdoped regime. And in the overdoped regime, what I just told you was that the resistivity has the power law changes, going from something that's linear in t to t squared. But in fact, if you take the derivative of the data, you actually see it's slightly more complicated than that. So this is the derivative of one of these curves here for this overdoped compound thallium-2201 with a TC of around 30 Kelvin. And if you take the derivative, what you see is a linear part here, the derivative's linear, but it has a finite intercept. And then this saturates at high temperature. So what that shows you is actually that there's two regimes. There's a high temperature linear regime. Then there's a region where it goes like t plus t squared. Now, if you do this decomposition as a function of doping, then you end up with a phase diagram like this. So you have this low temperature linear term that varies with doping. So there's two compounds here, there's LSCO and thallium-2201. So we have this low temperature linear term, and that seems to go to zero at around a doping of about 0.3, which in thallium-2201 is almost exactly where superconductivity goes to zero. So interestingly, it extrapolates almost to exactly the same place at LSCO, where superconductivity actually goes to zero at lower doping, but could be influenced by disorder. So you might sort of view this in some ways as a bit like the electron-phonon interaction in a conventional superconductor. So in electron-phonon interaction, you'd expect TC to be proportional to the strength of the phonon coupling. Well, here you seems to be proportional to the strength of this linear in T component in the resistivity. So you might then expect that whatever causes this is ultimately responsible for superconductivity, provided that you're willing to ignore the underdoped side of the phase diagram. Okay, so what about this? I said it's got this linear in T, but you've also got a T squared coefficient. So the T squared part seems to be almost independent of doping in this overdoped regime. So the fact that the resistivity varying between, so if you just look at the raw data, it starts off being linear, goes eventually like T squared. It's because the T squared term is independent of doping, whereas the linear term goes to zero at the edge of the dome. So eventually this one wins.
Question, is that also true for T squared or inverse wall angle? Cotangent of the whole angle? You find that T squared coefficient doesn't depend on delta.
That's a question I think I remember the answer to. It doesn't depend very strongly on doping. I wouldn't go as far as to say it doesn't depend at all on doping,
So,
but not strongly. It certainly doesn't do that.
okay. But it may not be as flat as what you're seeing in the other term.
No. From memory, in fact, that was one of the things I studied way back in the day. And there is a small change of doping. It's much less than the resistivity. So in the to a large extent, the changes in resistivity and changes in the Hall resistivity cancel each other out. to some extent.
So these data are all just about TC without the validity.
Yes, is the question. The answer to that question. Yeah. So these are so if we go to the very overdoped case, TC is very low. So we're not analyzing this part here.
Dashed line is just
It's just an extrapolation. Where was I? Oh yeah. So finally, this high temperature linear part. So there's essentially two bits to the linear and T resistivity. This bit and this bit. This high temperature bit also seems to be almost independent of doping. Maybe increasing a bit when in the endodopes part of the phase diagram, but essentially independent of doping.
And does the crossover from linear to linear plus quadratic vary with doping?
The crossover
temperature. Does that
this bit?
Yeah.
Yeah, I can't remember that, to be honest.
Presumably at optimal doping, there is no switch over to
No,
T squared, so it must
yes,
join.
it must join eventually. So the situation is quite nicely summarized here by this plot, which my colleague Jake Ayres made. So here we've plotted this T squared coefficient and then the linear coefficient as a function of doping. And here we've normalized to the number of planes in the unit cell and also the distance between the planes. And you can see actually there's pretty good scaling, apart from there's a curious factor of 4 for the thallium-2201. So LASCO and BISCO lie on the without any changes of scaling, lie right on each other. But for thallium, for some reason, you've got to divide everything by 4. And that's not really understood why that is. But nevertheless, that's the case. Okay, so if you look at optimal doping, the T squared term is very small. It's just basically all T. And then right over here, it's all T squared. But in terms of, is there some sort of crossover? Well, there's at least one here and possibly another one here. I forgot why I put that slide in now. I think it was just a demonstration of what you might expect to happen near a quantum critical point. So this is the barium iron arsenic phosphorus material, where you've got this fan of linear and T resistivity emanating out of this quantum critical point. So that doesn't appear to be quite exactly the same as what you have in the cuprates. So you don't really have this this fan, but rather a sort of a foot, if you like, where there's linear and T resistivity. Okay, so the other thing that I need to just say something about, because it may or may not become important later, you'll see why I say may or may not later, but there's also charge density waves in cuprates. And so these were first noticed by the fact that we could see quantum oscillations with a very small frequency, which is only 2% of the Brillouin zone, which implied that there was some sort of reconstruction of the large Fermi surface. And secondly, that the Hall coefficient, when we apply that large magnetic field, it changes sign. And this was conjectured to originate from a charge density wave, which was first seen in NMR measurements by Marc-Henri Julien's group, and then later using X-ray, first RICS and then hard X-ray. This is some data from Yuan Chang and my colleague Steve Hayden, where they're showing that the charge density wave intensity sets in, this is in YBCO, it sets in at about 150K. And it grows in a slightly unconventional way, not like you might expect from a traditional order parameter. And is suppressed when you go into a superconducting state, but if you apply a large enough magnetic field, then it continues to grow to low temperature. And this charge density wave has a Q of around 0.3, 0.3. And so if you apply that Q, biaxial Q to the Fermi surface, then you reconstruct it and form this little closed pocket around this point in the Friedland zone here, and that little pocket there is electron-like, which explains this change in sign. So this is just a picture of the Hall coefficient. So the bit I showed you before was a low field where it's superconducting at 100K. This is an underdoped sample of YBCO. You can see this where it changes sign and eventually saturates here. Okay, so just a couple more words about these charge density waves. The charge density waves are generally very short range. So this is a sort of summary of data which is taken from a review by Steve Hayden and John Tranquada. And this is the correlation length. And you can see that generally speaking, it's very low. It's around 20 angstroms. Apart from in LBCO, this is the lanthanum barium copper oxide at 1.8, where it becomes very long range. And also in YBCO, which has got the longest coherence length. But it's still, even in YBCO, it's still pretty short range. So the picture of what's happening here is that, in fact, that you're nucleating the charge density wave order around some impurities, and these patches of charge density waves grow, and eventually they start to touch. But we're still with phase shifts between them, and that's what limits the growth of the correlation length. So I think at low temperature, you can imagine that the belief is that most of the material has got charge order, but there are lots of discomensurations in the charge order. Okay, so we're thinking a little bit about quantum critical points, and an important milestone in this were these experiments that were done by Sven Badu and Louis Teifer back in 2016. And what they showed was they looked at the variation of the Hall number, which is essentially 1 over the Hall coefficient. And so in a simple model of the Fermi surface, simple Boltzmann-transport, you'd expect this to be proportional to a carrier density. I'll say a little bit more about that in a minute, about when that is is true. So in this plot here, we've got some data at low doping, which is actually from LSEO, where this varies proportional to the number of doped holes, P. Then there's a region where, as I just showed a minute ago, the Hall coefficient is negative. And so in this region, this is blocked out as green. So in this region, because of the reconstruction of the Fermi surface by the charge density wave, you would no longer necessarily expect it to be proportional to the number of doped holes. And then there is then a region just past optimal doping, where spectroscopically it seems that the charge density wave no longer exists. The Hall coefficient becomes positive again, and the Hall number undergoes this very rapid rise and seems to terminate around here, which with the what's the word? The eye of the believer, I think is a good word to say, starts to reach this 1 plus P line here. So it looks from this on this basis that the Fermi surface has gone from having P carriers in it to 1 plus P carriers, and the transition point is close to this optimal doping, or in fact magic number where the pseudogap opens at 0.19. However, there's a couple of caveats here. First of all, YBCO has zero chain, so it has, in addition to the planes, which where all this physics is going on, it also has one-dimensional chains, and that complicates the analysis of this, as I'll say a little bit more about later. The other thing is that it's got a very high He2. So although this all looks like the measurements here up to 80 Tesla, you're never really sure whether this is actually completely saturated or not. So if you look, there is a slight downward slope here on this data. So you kind of may think that if you went to infinitely high fields, you'd get a different result. But anyway, our first part of what I'm going to talk about is to investigate this overdoped region here. And we're going to do it in this compound, thallium-201, which has an advantage that it's a single layer cuprate that can be overdoped, and well, that's the main thing, and it's very clean too. Analyzing what the Hall coefficient means, we are generally using this. Well, if we know everything about the Fermi surface, then we can apply this semi-classical Schottky-Chambers-Turing integral formalism to calculate the Hall coefficient. And so basically what this is that you have an electron here, you have the Lorentz force makes it go around the Fermi surface, and then the conductivity is just the correlation between the current at time 0 and the current, the velocity at time 0 and the velocity at time minus t, and it's multiplied by this factor, which depends on the scattering rate. So you integrate the scattering rate, and then you have this exponential. So essentially, you've got an exponentially decreasing probability of the electron making its way around the Fermi surface, and that exponential decreases. The constant of that is the scattering rate. Okay, so if you apply this just in general, there's this very nice method of interpreting the Hall coefficient, which was due to Farnong back in 1991. And so he showed that the Hall coefficient in the low field limit can be, well, the Hall conductivity actually can be mapped simply in the following way. So you have the Fermi surface, and at each part on the Fermi surface, you have an L vector. So this is the mean free path, right? So this is VF times the scattering rate. And this L vector, as you go around the Fermi surface, is always perpendicular to the Fermi surface. And it traces out a curve in L space. And Ong showed that if we look at the area of this curve in L space, so if you imagine here, we're all along the x-axis, so we're at this point here, and here we're all along the y-axis, so we're at this point here. So in fact, all of this curve is essentially determined by what's going on at this little corner here, where we're going from this point around to this point here. So Ong showed that the Hall conductivity is simply related to the area of this L space. So it's effectively the conductance quantum times the flux threading this, so fields times this area, divided by the flux quantum. And that is the Hall conductivity sigma xy. And sigma xx, which is the longitudinal conductivity, is just the average of this L as we go around the Fermi surface. So S in this case is the circumference essentially. And then once you've got these two components, you can work out the Hall resistivity, which is just the sigma xy over sigma xx plus sigma xy squared. And in the low field limit, you can forget that. So it's just this over this. So in general, it's quite a complicated thing. But if you have a spherical Fermi surface and isotropic scattering, then you get back to the very simple relation that RH is 1 over NE. However, if you've got strong anisotropy in L, then this is no longer true. So in general, interpreting the Hall coefficient as a carrier density is a complicated thing. However, in the high field limit, all of those complications go away. So in the high field limit, your electron's going all the way around the Fermi surface, hopefully multiple times, but at least at least a couple of times, you would hope. And in the high field limit, that basically averages out all of this anisotropy, and you end up with RH going back to 1 over NE again. So in the Boltzmann picture, we can interpret the Hall coefficient in the high field limit in a single, when you have a single band at least, directly in terms of the carrier density. So going back to this data here, very shortly after this was published, there was a bunch of papers which tried to understand what was going on, and they all relied on some sort of reconstruction of the Fermi surface. So first off the block was James Story, who used a Yang-Rice-Zhang model of the pseudogap, which is effectively a reconstruction of the Fermi surface. So you have this big Fermi surface here, which is then reconstructed along essentially an antiferromagnetic rebound zone, and you end up with electron and hole pockets. And if you calculate the Hall coefficient, he did it actually in the weak field limit, then you get something that looks quite like the data. So you get this this transition from P to 1 plus P. So there are other versions of this, although using different types of order, except there was never really any clear experimental evidence for actually any of these orders. So in this case, what you could say is that the interpretation of this transition was linked inextricably to the appearance of the pseudogap. Okay, so what we're going to now look at is how this evolves in this region here. So our weapon of choice here is overdoped thallium-2201. And as I said earlier, this is a single layer, it doesn't have any chains, it's electrochronically clean, and unlike Lasco, for example, there are no Lifshitz transitions. So if you do a DFT calculation, and I'll explain to you why you can believe that in a minute. If you do a DFT calculation, you'll find that the Van Hove point, so the point where the Fermi surface becomes electron-like, is where it's very heavily doped. So it's experimentally, you can't get over here actually. So the furthest you can get to just about 0.3. So it's almost double the experimental range of doping here where you'd expect electron-like. No Lifshitz transitions, and this old work by back in the day, Andy Mackenzie here, shows that the residual resistance in this material is the lowest of all cuprates. So it's only about 6 micron centimeters, which implies very large mean-free path of around 1,000 angstroms. Okay, so what do we know about thallium-2201? Otherwise, so some experiments by Nigel and myself back in 2003, we did some angle-dependent magnetoresistance measurements. So what this involves is taking a crystal, applying current along the c-axis, and measuring c-axis resistance, and then varying the field angle. And so when you do that, when you do that, you make the electrons undergo cyclotron motion, and you average over different velocities as you change the field angle. And what that does is it makes the c-axis magnetoresistance vary. So it's a bit like the angle magnetoresistance oscillations which you see in organics. But here there are no oscillations, it's just a variation. So here you can see on the left is the data. So this was taken at a sample of TCF of 20 Kelvin, magnetic field 45 Tesla, temperature of 4.2 Kelvin, with omega C tau is around 0.45. So not really quite in the high field limit, but getting there. And this on the right-hand side is a simulation of that same data using the Schottky chamber tube integral formalism. So you can see it reproduces it really well. And what I'll explain in a minute what the fitting parameters are in that. But essentially, all of the fitting parameters are just the shape of the Fermi surface.
You have to include a lot of anisotropy in the scattering rate.
In this initial data, no, there's none. Later, there is. Which brings me on to this. So, if you did this simulation at low temperature, then this fits really well with no additional parameters. And but if you then increase the temperature, you find that the shape of the amaro changes, and it changes in a different way than just changing omega c tau. So if you just do this same experiment at just the same temperature but lower field, then you get the features diminish in size, but they don't actually change in position. Whereas in order to fit the data at higher temperature, what was necessary was to invoke an anisotropy in the scattering rate. What was necessary was to have an anisotropy where one part varies like t squared and another part varies linearly in t. So basically you have an isotropic part which varies like t squared, so that's everywhere the same, and then an anisotropic part which has got this kind of fourfold shape which varies linearly in t and is maximal along the antinodal direction. And then later, we showed that if you then vary Tc, then this isotropic part basically didn't vary at all with Tc. And so this is essentially the doping, whereas the anisotropic part effectively almost perfectly linearly scales with Tc. So this is basically similar to the linear component of the resistivity, and this is the t squared component of resistivity. If you remember that earlier, I told you that this one, the t squared component doesn't vary with doping, and this one, the linear component, varies linearly with doping.
Can I ask you a question?
Yes.
So this is actually, this is for the skewed formula where you have like an angle dependent scattering rate.
Yes.
But if I have a diffusive transport, if I have a particle bouncing off, this, it might be a totally trivial thing that we should probably explain to your students, but I was trying to explain something to somebody and I realized I don't quite get it myself. So if I have a particle flying in, like in real space, and it's scattered all over the place, what do I care what the initial kind of direction was? If it basically equilibrates and start kind of scattering, then you know what I mean? If you have a ultimately diffusive transport for a long time. So it's not like I have a canal approximation where the particles are only flying like a ray.
Yeah. Agreed. So was there? So your question was?
The question is why I should be allowing for the angle dependent relaxation times, where for diffusive transport it should average out the whole.
Well, I mean, the simple answer is you haven't got diffusive transport.
You have not got.
Yes.
What do you got instead?
Well, I mean, you've just got, regular coherent transport. So, the fact that you could.
No, this is direct scattering rate, like, but basically particle can bounce off sideways of the impurity.
Yeah.
Why I'm not getting it?
So,
Years.
Okay, I'm not quite sure I understand your question, but could you try?
Sure.
All transport beyond the mean free path is diffusive.
All transport beyond the mean free path, what do you mean?
Meaning, once you look at the
Like a
physics
couple of
scales longer than the mean free path, the transport is diffusive.
Yes, I would imagine that is true.
I'm just saying something silly, but I don't know how this connects with Sasha's question.
My question is why I'm allowing for, I understand the fitting parameter in the equation, the formula, but physically, if I have a diffusive transport, unless it's the ballistic, because this looks to me like ray optics, this looks to me like a canal approximation. Things are only flying along a certain direction and never deviate.
So, I mean, maybe I'm thinking of this too simplistically, but I would say that, the distinction between when you've got, coherent transport and diffusive transport is when the mean free path exceeds the off-radial limit. Or is less than the not yet, so when the mean free path is less than the lattice spacing, then you move over to a diffusive regime. But here you've got a coherent regime, you've got a conventional metal.
So if I have a wave packet, let it run for a minute.
If you've just got a conventional metal,
Yeah.
the anisotropy and scattering rate comes into the semi-classical equations of motion.
I guess that's exactly, maybe we should do it after you will tell me in the blackboard. I'm sure it's a trivial thing. I just don't have a mental snag. If I'm flying in for a wave packet for a minute.
Yeah.
For sure, I have a lot of bouncing around. How come I'm not averaging over the whole direction thing? That's my question.
Chris has got his hand up. Maybe the solution.
Shall I chip in a potentially clarifying comment?
Okay.
So point is, you need diffusion to get a finite conductivity at all. Right? Otherwise things just accelerate forever. But once you've got that finite conductivity, it's given by the time integral of the current path. And that's dominated by relatively early times when the currents are still pointing in roughly the same direction. So the bit that you're talking about exists, it makes the integral converge. But the value that the integral converges to is set by relatively early times when these things are still kind of going on here.
So then it's another body, depending on which way I kick my wave packet to begin with.
I suggest that this topic, although it may be important to solve it,
Yeah.
strange metal problem.
Now that we don't understand this, let's move on.
Okay, so then later we saw that the
Areas wants to make.
No, not a question, not related.
yes.
So in NSCO, just remind me, I thought there it's reversed, so the claim is that the constant part is anisotropic and the T-linear part is isotropic. Is that true?
So this is some recent data from Louis' group
Yeah.
in neodymium doped LSCO at one specific doping. Yes, you're correct. But in that case, you've got a strange situation because you're at very close to the Van Hoek point. Right, where you've got very anisotropic scattering at one single point. So the nice thing about thallium is that none of that complication exists because of the Van Hoek and so on. But that is an interesting other example of this sort of thing, but in my view, it's not a very general one. Okay, so we also managed to observe quantum oscillations. So these are some nice quantum oscillation data. And we did this for only the most overdoped samples. So I'll come back to this later. But basically, very overdoped samples, so TC about 10K. And after a lot of trying, we eventually found quantum oscillations in higher TC. But this was the limit. So we must have measured more than 100 samples over the time. And we're still trying, actually. In Toulouse using the new tunnel diode methods, and fields are now up to in excess of 90 Tesla. New samples, etc. We've not given up. We're still trying, but we've never ever seen quantum oscillations in higher TCs. Okay,
Give us a number for the dingle field.
I can give you a number for the mean-free path, which is perhaps more useful. Okay, so it's of order. So I said what the mean-free path was earlier based on just resistivity. If you do it from a dingle analysis, you typically get numbers that are between 300 and 500 angstroms. So quite long. These are high-frequency oscillations. So these correspond to the 1 plus P Fermi surface. 18 kilotesla is a very high frequency. So this is a big Fermi surface. And there's also this ARPES data, which I'm not going to say too much about, but the ARPES data, which has never been reproduced, actually. A number of people have tried. Thallium-201 really doesn't like to cleave. I don't know how these heroes did this back in the day, and they're not sure they can do it again. but they did manage to get this data, and it shows a nice coherent Fermi surface. Okay, so we were also, from the quantum oscillation data, able to measure the effective mass, and we found that the mass is around 5, which implies a renormalization of about factor 3. We could also look at the variation of the amplitude with angle along various different directions. So this is going from the c-axis to the a-axis, and this is going from the c-axis to the middle of the a and b axes, and you get a different pattern. And you can fit this with as exactly like we did with the angle-dependent magnetoresistance by using this cylindrical harmonic parameterization of the Fermi surface. So basically, you start off with a circular tube, then you add fourfold anisotropy. This is K40. Then you can also add this kind of twist, which is K21, so-called snake that swallowed the chain term, and so on. And then the interesting thing is that at the end of this, we come out with some numbers, and you have to look at it carefully to look at all these. So this is what we get from just a regular out-of-the-box V2K DFT calculation. And these are what, so forget about K00, because this is fixed by whatever I decide to dope my DFT calculation to, that's irrelevant. But actually, these warping parameters actually come out pretty close to what you actually find in the experiment. So the interesting, I guess the thing is here that DFT actually does a pretty good job of describing the Fermi surface, and even all these very small wiggles in there. Oh, and also you get pretty good agreement between what we found previously from the angle-dependent magnetoresistance and also the DHVA later on. Okay, so also
You showed a spin 0.
yes.
What does that tell us about the spin orbit coupling or the anisotropy of the G factors? In fact, it looks like there's more than one if I look further.
Actually, there's only one spin 0. So there's no, this is torque data actually. So there's an overall envelope, so it's 0 here because of the torque factor. It goes down because effectively dingle effect, right? So the orbits get bigger as you go to high angle. So this is why this decays here. Then you get these what we call geometric beats, which comes from this term here. So you get basically it's where you get destructive interference between different parts of the extreme orbits, and that gives you a 0. But I'm stalling because I can't remember the answer to your question. It is actually, if you've only got one spin 0, it's a bit ambiguous because you really need more than one to nail it down, because it's indeterminate by factors of pi. Right. But I think actually now it's slightly coming back to me. I think this actually. Now, okay, so apart from this indeterminate factors, if you just put in the bare band mass and don't think about anything clever, I think it comes out about right.
But there has to be a spin anisotropy, right? You get an isotropic G factor.
Yeah.
How would we get a spin 0?
Well, okay, it depends on how you parameterize it, but normally you think about, if you just put in a G factor of 2 and then a mass that varies with angle.
I thought that would do it. Thank you that you explained my question. Okay.
So the other thing, so we should be relevant for later on. How much time have I had, by the way?
Well, we're coming into drinking time.
All right. I'm barely going to move on.
We started late, so I think you've got another
20 minutes. 20 minutes, okay. I'll get on moving on, because I haven't got to the new stuff yet. So this is some old data by John Lauren, God rest his soul. And this is heat capacity data for this thallium-221. And the interesting thing about this is that the people who believe there are quantum critical points near optimal doping, there appears to be very little variation in gamma. So this is various different TC. So this is optimally doped going to very overdoped. And this is the total measured gamma, and it doesn't vary very much.
Can you remind us how the photonons were subtracted?
I can, but not. I can remind you in the pub later.
Okay.
It's a long and involved
It's
story.
remarkable that you can even do it.
It is. That is also a little bit consistent with this. So within the error, we didn't really see much variation in mass, although we didn't really change DC that much. That's from alpha. And yeah, one interesting thing that was nice is that this peak capacity data was done about how long? 20 years before we did the de Haas-van and in fact, the masses agree. So John wasn't completely stupid with his phonon subtraction. Okay, and then there's some other NMR data here, because from what I'm going to tell you about, the question of whether or not there's a pseudogap is relevant. So this is some NMR data, and from thallium 2201, and these are various TCs, and these are night shift data. And if there was a pseudogap, you'd expect to see a downturn in this night shift, and you don't. Except perhaps at the very highest TC, there's a slight downturn. And this would be consistent with the pseudogap opening for doping less than 0.19, which would be similar to what the case is in YBCO. Okay, so onto the Hall effect. So what we did was do some Hall effect measurements on various different dopings of thallium 2201. And we did this in high field up to about 65 Tesla. So a couple of things of note in the data. If I look at the most overdoped case, you'll see that at the lowest temperature, then the normal is almost completely flat with field. And at higher temperature, there is some field dependence, and there's also some temperature dependence. And if you scale these with the normal state resistance, so what you might expect to do if Kohler's rule was being obeyed, for example, you can see that kind of the high temperature data is kind of following a path which was kind of extrapolated down to this zero temperature limit here. Okay, and back to the Schottky tube integral formula, we can actually simulate what we'd expect from the parameters we got from the de Haas-van and the angle dependent magnetoresistance. We can work out what we'd expect for the field dependent Hall effect, and essentially this looks exactly like the data. So what you find is that you get an enhancement of RH here, which depends on temperature, because of the anisotropy of the scattering rate, and at very high field, that all gets wiped out, and it goes back to this dotted line, which is equal to 1 over NA. Okay, so we did this Hall effect measurements at various different temperatures, and we took the very highest field, in all cases, the high field limit, and plotted that. So this is at 65 Tesla. We plotted that versus temperature. And then we took from this the zero temperature limit, which is easy to do here, 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 and here. Gets a little bit more uncertain for the highest TC samples because we run out of magnetic field. However, when we've done that, we end up with this diagram here, where this is the Hall coefficient, Hall number versus doping. And what you see is, like in the case of YBCO, we see this switch from P, the Hall number being varying like P, to the Hall number varying like 1 plus P. But unlike the case of YBCO, it does so over quite a broad range of doping, and also in a region where there is no pseudogap. So we did a similar type of analysis and measurements with another cuprate, which is the bismuth 2001, another single layer cuprate. This one's a lot more disordered, has a lower He2. And again, this seems to follow the same behavior. So finally, we put on the data for YBCO on the same plot. And so you can see that the data for YBCO has this large increase here, whereas we have this much broader case here. But if you remember, I told you that there's the chains in YBCO. So in the chains, you have two parts to the conductivity. You have a part that's due to the chains and a part that's due to the planes. And if you take the simple model that the chains are purely 1D, then you have a chain part which doesn't have a sigma xy, and it doesn't have a sigma xx in the chain direction either, in the direction along the chain. And so in that approximation, if you just want the plane Hall coefficient, you have to take the data that you measure and multiply it by the anisotropy and the resistivity. It's essentially because there's current being carried along the chains which doesn't have a Hall response. And if you do that, then the YBCO, okay, so if you do that, but with the caveat that we don't actually know what the anisotropy is. So if we take some data, which is actually at zero field, it hasn't been measured yet at such high fields, but this is zero field data for this anisotropy, and you just scale it in this way, it actually falls almost perfectly onto the same curve as for thallium-201. Okay, so what does this all mean? Well, we thought that possibly we had a solution, which was my colleague Steve Hayden discovered that in some compounds of overdoped thallium-201, there was he saw a charge density wave. So his charge density wave he saw actually had a long correlation length of around 200 angstroms. It has a Q of about 0.31, which is similar to YBCO. And the onset of where this happens in the phase diagram seemed to correlate with what we see in the Hall coefficient. However, one warning here is that the latest information from Steve is that this seems to be sample dependent. So he doesn't see this in all samples. So there's some question mark over whether we actually believe there is a charge density wave in overdoped thallium-201 or not. This data looked like fairly clear. There were 3 different samples, but we've also had samples where there isn't any clear signal, which then makes us worried. So that's still something that's under investigation. However, if we do believe there's a charge density wave, then we can calculate transport properties. So we do this in the normal way by diagonalizing a very big matrix. And if we do that, then we have, it ends up that the Fermi surface is reconstructed, and you get hole pockets, electron pockets, and open sections of Fermi surface. And as you crank up the potential, then you make the electron pockets smaller, and eventually it disappears. And as I'm running out of time, I won't go through all of this, but the bottom line is you then can calculate the Hall conductivity. And what happens is that, in fact, as you crank up this CDW potential, you get something that almost looks similar to the experiment in the sense that it starts off at around 1+ p carriers, and as I open up this gap, it decreases markedly. It ends up not exactly, but approximately close to NH = P. So this is a possible explanation for the data, but as I said, it's not for certain that this is the case. So where are we? Okay, so the last thing I want to talk about is I've got probably about 10 minutes or something like that. Yeah. So the last thing I want to talk about is magnetoresistance.
If you want to have discussion, we can do discussion.
Okay. So I'll try and speed up. So we've also want to talk about magnetoresistance. So we looked at the Hall coefficient, but another thing that you could worry about is the longitudinal magnetoconductivity, and we talked about the linear in T response in the resistivity, but there's also a linear in H response in resistivity. So this is some data in LSCO. It's published in 2019 by Giraldo Gallo et al. And it shows that there's this linear in H term. This is LSCO. And the linear in H term is approximately independent of temperature. So even though the scattering rate would have seemed to have varied a lot, the linear in H term doesn't appear to have changed at all, which is not what you'd expect from conventional magnetoresistance. So this is our own data for thallium-201, which shows the same thing. Here you have the magnetoresistance, and you can see that up to, as you change the temperature here, the slope of this linear in H magnetoresistance doesn't hardly varies. There's some other strange things is that it doesn't appear to depend very strongly on whether you've got impurities in there either. And it also doesn't seem to even depend on which direction you put the magnetic field in. So it's a magnetoresistance, but it doesn't behave like a normal magnetoresistance. And in fact, if we try to model it with the good old Schottky tube integral formula, that gives an answer which is completely wrong. It doesn't look like the experiment at all. So the slope you get out of this, it's not, you don't get a constant, this is the derivative, you don't get a constant slope, it's not H linear, and it varies a lot with temperature, which it doesn't in experiment. So we've got a bit of a conundrum here because we've got, going back a few slides, we had the c-axis magnetoresistance, which is the thing we modeled to get the angle-dependent magnetoresistance, which gave us a lovely shape of all the Fermi surface, which is confirmed by quantum oscillations. So that was modeled by this. We have the Hall effect, which also seems to be well modeled by this, at least at low temperature, but the magnetoresistance doesn't. That's a mystery, which we don't really have an answer for. So one other way of looking at this is this so-called quadrature scaling. So this is data from Barium 122 from James Analytics' group, and they also discovered that in this material there's the critical doping of 0.13 or 0.31. There's a linear in T resistivity and a linear in H resistivity, and the two things scale together if you plot the data as H over T. So you have essentially the scaling factor and everything scales onto each other. We can do a similar thing for the thallium case, but in this case, we need to take the derivative of the magnetoresistance, and then this does scale like H over T. So if by taking the derivative, you're effectively removing the T squared component from the resistivity. So the linear part of the resistivity seems to scale, whereas the T squared component doesn't. And then the final thing I was going to show is this graph of how the linear in H component, so this is the linear in H coefficient in Bisco, Lasco, thallium-201, how that varies with doping. And then on the right panel is the linear in T resistivity. And you can see that actually they're very strongly correlated. So the linear in H resistivity seems to occur wherever you get the linear in T resistivity, and both seem to vary in a way which in some way resembles the electron-phonon coupling in conventional superconductor. Okay, so there I'm going to stop. I'll just throw up a few view graphs. So we have this c-axis magnetotransport, well described by this Boltzmann formalism. Quantum oscillations show that the Fermi surface for the overdoped case is close to what you'd expect from DFT. But crucially, for doping less than about 0.26, we can't see quantum oscillations. So in my phase diagram, this is the bit here in yellow. So where we have the Hall coefficient equal to 1 plus P, we can see quantum oscillations. We can describe the angle magnetoresistance c-axis. But in this region, the Hall number falls. We don't see quantum oscillations, not yet anyway. And we can't any longer fit the magnetoresistance, the c-axis magnetoresistance. So Yeah, and then finally, this in-plane magnetoresistance is another mystery. It seems to obey H over T scaling, which implies that the field and temperature are kind of conjugate variables, but it's not described by Boltzmann theory. And then, yeah, I think I'll stop there. Thank you.
Questions? Great. Yeah, thanks. Great talk. Is there any theory, Boltzmann or not, that gives that square root of h squared plus t squared?
Not a microscopic theory. There's some sort of phenomenological things where you kind of okay, no, that's not entirely true. There are some microscopic theories, but not ones that work in all situations. So there's one that was invoked to try and explain the barium material in the iron base thing, which was based on essentially sharp bits of Fermi surface. So effectively where you exceed the weak field limit at all fields. But there's certainly no such thing in some of the other material, and certainly not in thallium-221. There have been also things which have been conjectured to do with electronic inhomogeneity. But again, that's difficult to reconcile with material that has long mean-free path and shows quantum oscillations, etc. So, no. I mean, you know, there's theory on the sort of phenomenological grounds that this is all to do with Planckian dissipation. I don't know whether you'd consider that to be a microscopic theory or not.
Just the phrase Planckian dissipation, probably.
So, I mean, the idea is that, you know, you have maximal you know the story, right? But for the benefit of everybody else, you have a maximal scattering rate, which is determined by the temperature.
But then how does that work with the field? That means the field can substitute for the temperature and alter that.
Yeah. Well, yeah, and
B is a state. One would imagine it means it's a kind of scaling variant system, right? In which field or magnetic field substitute for each other, right?
there are a number of, as I sort of alluded, but perhaps hasn't been given enough attention. There are a number of other strange things, such as the fact that this slope doesn't seem to depend on temperature or impurities, right? So you can have Bisco 2201, which has got 10 times the residual resistance. It's got exactly the same linear in H slope as thallium-221. It also doesn't appear to depend very strongly on field direction. Hence, where's the Lorentz force? So there's a number of odd things which are not obviously explained. But the odd thing is that clearly there are parts of all of this problem that are described by conventional Fermi liquid Boltzmann transport. So it's, my colleague Nigel, if he was giving this talk, is very much into, there are sort of two sectors, an incoherent sector and a coherent sector, and one behaves like this and the other behaves like that. And so depending on what sort of experiment you do, you couple either as a coherent sector, which gives you the Fermi liquid part, that's all the T squared part. And then you've got the incoherent sector, which is the linear in T, linear in H. And, Nigel would argue that that is the bit that's superconducting. So he wants the incoherent part to be superconducting.
But then why no hostile? It's all electrical channels.
Other questions? Yes, please.
So maybe I missed this. So this scale invariance with H over T, that's only true in the region where you have linear. It's not, so for example, when you go overdoped.
So this is
not to have T square.
yeah, no. So okay, so Yeah, I was rushing a bit at the end here. So this is the region where you've got t squared. So if you do straight h over t scaling, it doesn't scale. So if you just subtract off the residual resistance, then the magnetoresistance doesn't scale, right? But if you subtract off the temperature dependent part of the resistance, so in other words, you're effectively subtracting the t squared component, so you're only scaling that part of the resistance that varies linearly in t, then it does scale. So it's like as if only the linear part of the, so if you imagine you had two conductors, as it were, one which had a magnetoresistance which obeys h over t scaling, and the other part which is essentially a conventional metal. Actually, one thing I didn't point out was another thing about this. If you actually calculate what the magnetoresistance is, not only has it got the wrong behavior with field and temperature, it's also much, much smaller. So it's 10 times smaller than what you see experimentally, or 5 times at least. So it's likely then what you've got is that what you're seeing is the response of the linear in t component, and what the other bit doing is just irrelevant. So then the question that, if you think about it for a minute, is why doesn't A short out B? And so that is not very clear. You can develop a model where, again, which I don't really like very much, but just for the sake of argument, where you've got a kind of a real space mixture of the two things. So if you've got like an effective medium theory, where you've got conductor A, which is got linear in T resistance and a H linear magnetoresistance, and then a Fermi liquid part, and you mix them together in an effective medium theory, then you can replicate what you get.
Does that mean coupling them in series or parallel?
Well, it's a 2D effective medium. So what does that mean? It's both, really. Imagine you've got like, I mean, I like to think about it like as if you've got, you're on the beach and you've got white and black sand and you mix it together. So, you know, black is one and the other is white, right? So it's like a resistor network, as it were.
Yeah, both series.
Yeah.
Good. I saw other hands up. You named the other question. Yes.
Yeah, actually, maybe it's a bit of a shot in the dark trying to understand the theory and experiment here. Maybe my eyes are deceiving me, but I could see that the bottom left corner of the right panel could somehow reproduce the left panel. I'm sorry, of the two central ones. So it's as if everything is normalized. If the effective field in that case would be, 5 to 10 times smaller than the actual wide field. Would there be any reason for that? Would one think in terms of flux per unit cell in the context of the density of the cluster? Would there be any?
No way I can think of within a conventional way of analyzing the data. No.
Because no, it looks like the trend link, the trend is right, but it's just a matter of speed. To renormalize your H, then the factor you would get.
Yeah. So you mean if this was if you plotted this up to 2 Tesla instead of 20? Yeah, maybe, but there's no physical reason for that. And also, you'd also got to do something about the magnitude, which you can see is about a factor of 10 too small.
Let me ask you this. This is a very nice summary of magnetotransport. Of course, there is a broad spectrum of other experiments that have gone on in the system. For example, Peter Abamonte has looked at the compressibility of the system. And he sees phenomena which are in approximate accord with the marginal Fermi liquid hypothesis. So I guess my question to you is without theory, is there a way of incorporating the different experiments to create a challenge description, phenomenological description of the cuprates that could be used as a basis for future theoretical attempts. In some sense, what we'd like to do is characterize the correlate, as Chris was saying, the correlations, the charge, the spin, the current, and to get a picture of what we need to understand the microscopic system. And in that respect, other materials are important. For example, has anyone done the kind of high field measurements we're talking about on cerium cobalt indium 5, which of course means only going up to 5 Tesla. But presumably one could look at whether quadrature works there. That's a system that was claimed to have all the strange metal properties, including the Magneto-transport. It'd be very nice to know whether it transitions to that case. And also in that respect, Moiré systems. It's an infuriating situation that the Moiré experimentalists, every time I ask them, can they give me a definitive answer on what happens to the Hall constant at 100 temperature? They always say, well, we haven't quite analyzed our daily there. I don't know what's wrong with that. I've been asking this for about 2 years now.
Well, you're going to have
in Ohio.
You're going to have ample chance to do that in the next couple of days, right? You've got the very man.
That's true. But there's need for an overarching comparison of different systems.
I think there is some. I mean, there's a good point about cerium cobalt indium 5. I don't know the answer to that, but I mean there is some. I think coming together of cuprates and ion-based systems.
Yes.
I think one is a good analog for some aspects of the other.
Yes.
How that fits into the bigger picture heavy fermions. I mean, there are many things, but I can't answer the exact question about that. And also, I need to think about the compressibility also.
Y-bore is another material, right? Terbium, boron, aluminum. That's a system where we actually, the suggestion for the quadrature, I made it a gym because we've done it on terbium, boron, aluminum.
Yeah, okay.
And but there we can't, because of the nature of the samples, it's difficult. No one's ever done Magneto-transport measurements. Curiously, that so we don't know whether it does the same stuff as this or not. There, so I think more effort on comparisons and older systems which are deemed, old-fashioned, and therefore you don't it's very badly needed to connect up the fields.
Excellent suggestion.
Okay, I'll diatribe. Any more questions? I think we will now adjourn. First of all, we'll meet again tomorrow at 10 o'clock in the morning. But for those who want to join us, we're going to be going there now. Yeah.